Let's spend some time with our good friend, MCT. So here's a sequence, 1 over n. Let's show that it converges using the monotone convergence theorem. We can write down the statement an is trapped between 0 and 1, and that seems pretty obvious. Writing it out, we can see that on the lower side, 1 over n is a positive quantity. We can strengthen that by showing that this is equivalent to 0 being less than 1. Pretty good. On the upper side, plugging in for an, multiplying both sides by n, that this statement will be true provided that n is bigger than 1. Pretty good. Collect that together. The statement that an is bounded between 0 and 1 is the same thing as 1 is bigger than 0 and 1 is less than n. Very good. So the sequence is bounded. The second thing required by MCT is the M, monotone. Let's show that the sequence is decreasing. Again, that's pretty obvious, but let's deal with it in a slightly more rigorous manner. So we have the inequality that the next term is smaller than the current term. The next term is the reciprocal of n plus 1, and the current term is 1 over n. Looks pretty obvious. Looks like we can just walk away. Do a little manipulation, and we can bring it down to the idea of adding 1 to a value increases the value. Another way to show that a sequence is monotone is to look at the difference. If the next term is bigger than the current term, then their difference will be negative. So, plug in for the definition, combine into one term, and you can reduce it down to the statement that negative 1 is negative. Pretty nice. Yet another way to show that a sequence is monotone is to consider the ratio. If the next term over the current term is less than 1, then the next term must be smaller than the current term. Plugging in and then manipulating, we're returning back to a previous computation. We can improve on that previous computation, and we can subtract n from both sides to come up with the statement that 0 must be less than 1. Pretty nice. Yet another way to go about showing that a sequence has a monotonic property is to look for a function which agrees with the sequence at natural numbers. Take a derivative of the function. In this case, we're getting that it's negative. Therefore, the function is a decreasing function, and the sequence inherits that same property. Good. 1, 2, 3, 4 different ways in which you can approach the notion of monotone. Fantastic. We've shown that it's bounded, that it's monotone. Bounded, monotone. We may therefore apply MCT, and MCT provides that it will converge. MCT doesn't tell you what it converges to, only that it does converge. Nice. Do one more example where we'll do an algebraic computation of the actual limit. Let's consider this sequence, which is recursively defined. Let's run through MCT once more two different things to show. And for the first bounded condition, we're going to use an inductive argument. So here's what we want to show. We're starting positive, we're taking positive, adding positive, so the lower bound is by inspection. For the upper bound, let's do the inductive argument. Here's the statement that we want to show as being true for all n. We need the base case. 1 is less than 2. Check. For the inductive step, assume that it's true for n equal k. Now, let's use the recursive definition to consider what the next term is. A sub k plus 1, by the recursive definition, is half of the previous term plus 1. But half of the previous term, on the assumption that p of n is true for n equal k, a sub k is less than 2. So this quantity is 1 plus 1, is less than 1 plus 1, and 1 plus 1 is 2. Therefore, we've shown that a sub k plus 1 is less than or equal to. Very nice. By mathematical induction, we've shown that p of n is true, thus establishing the upper bound. Good. MCT we know requires monotonicity. We're going to use the fact that we just established that an is bounded above by 2. Multiply both sides by a half. Add half of an on both sides. And then on the left, half plus a half, you have an. And on the right, you have the recursive definition. And this is exactly the idea of monotonic. Sweet. Therefore, this sequence will converge since it's bounded and monotone. Very good. Now we're at the point where we're ready to find what it converges to. So we'll manipulate algebraically. So just a restatement, MCT, an is going to go to L. And if an goes to L, then a sub n plus 1 will also go to L. So in the limit, we can swap out both of these terms for L. And then algebraically manipulate, move half L to the other side, multiply by 2, and find that the limit is 2. Bring all that together, make a statement, and done. Excellent.